sometimes you're going to be asked to find the limit of a piecewise function. And in this case, I have a piecewise function here, and we're being asked to find the limit as x approaches 1 from the right, as x approaches 1 from the left. These are two different examples. Now, what do we know about the right side of 1? Well, the right side of 1 is when x is greater than 1. So, when you're approaching 1 from the right, x is greater than 1, this is the function we pay attention to. And as we approach as we approach 1 from the left, what do we know about the left side of 1? Well, the left side of 1 is where x is less than 1, and this function is going to represent that. So, if I want this limit as x approaches 1 from the right, I'm going to go over here and look at this. This is a linear function, nothing weird about it. As x approaches 1 from the right, I'm going to be riding along this function. This is me doing this problem without graphing it. You can definitely go through and graph it. I definitely suggest you do that. But for right now, I'm just going over the basics, okay? So if you need to practice graphing your piecewise, press pause, try to graph this, and then we'll compare your picture with the answer we'll get, all right? So here, x is greater than 1. Plugging 1 in here. I know it's not or equal to. That's fine. For a limit, it's all about what you're getting closer to, not that you actually get to that value or not. That part doesn't matter. So if I fill in 1 and evaluate this function here at 1, this piece of it, I'll get negative 3 times 1 is negative 3. So the limit from the right-hand side is negative 3. Now the right side, as we approach, I'm sorry, that was the approaching from the right, yes. This is the left side. Now for the left. So if we're approaching from the left, we're approaching along this function right here, x squared, filling in a 1. It's not a negative 1, so that's 1 squared, which is 1. Here, I have the limit in general, okay? It's not asking us to approach from one side or the other. It's really doing both. From the left I'm approaching, or from the right side I'm approaching, I get negative 3, but from the right side I'm approaching and I get 1. Well, what does that tell me? As I approach from these different sides, really, I guess I should go this way, you're approaching. This one I came from the right, I got negative 3. I came from the left, and I got 1. They don't match. You're not approaching the middle. You're not approaching both of them. Your limit will only have one answer, kind of like a function. So you would write does not exist, or you can write just DNE. Okay? So that limit does not exist. If you want to see what that graph will look like, I'm about to show it to you. I'm not going to show you the work. So if you don't want to see it, hit pause and draw it if you didn't do it yet, and then when you come back, I'll promise it'll be graphed. So here we have the piecewise function that is described in f of x above. So you can see as we approach from both sides, you're approaching two different numbers, and that means the limit does not exist. Okay, so for this next question, it just asks us, evaluate the function at the indicated value. Now you really don't need the graph for this. You can just do this from the piecewise function, or you could just do it from the graph and don't need the function f of x written out itself, okay? So what do we know? We know that this is asking us, what does y equal and x equals 1? Neither of these domains includes 1. That means it's undefined. Usually we don't use the phrase does not exist. I guess you could, but I would rather write undefined, okay? For a limit, I use the phrase does not exist when there's no answer, and for a function, when I'm evaluating, if there's no answer, if there's no y value for a particular x value, I just write undefined. It's not defined for the x value of 1, therefore the y value that goes with it is also not defined, and that is all. Here we have a few more limit examples, so we're going to be approaching 6, 0, and 1 of this particular function. Now, if you fill in, there's a few things you need to know if you're going to try to do direct substitution. If you get 0 over 1, or really any number, if you get a number over 0, and if you get 0 over 0, these all mean something different, okay? So what do these all mean? If you get 0 over 1, that is okay. It just equals 0. But if you get a 0 on the denominator, so you have a number over 0, that's a big no, all right? It might mean it's undefined there. That might mean you have to draw a graph or use tables, but that's going to basically tell you you're probably approaching either infinity or negative infinity, or the answer will be DNE, okay? So maybe one of these will be your answer. Obviously, it's a case-by-case basis, but something along those lines. And if you get 0 over 0, what you need to think about is that it kind of looks like, this is an arrow, okay? It kind of looks like a division sign, and you probably can divide out a common factor from top and bottom. That means there's a hole in your graph. That means when you cross that out from top and bottom, you're really spackling the hole, and then direct substitution will work after that. That was a whole mouthful, but hopefully that all either rings a bell if you know this already, and if not, hopefully after we do these examples it all makes sense. So what I'm going to do above this example and a little bit of the extra space on top of the page is I'm going to factor it just to save time as we work out this next example. The denominator looks pretty good to factor because I have a 1x squared. So what multiplies to 144 and then adds or subtracts to 13? So 1 and 144, 2 and 72. I'm just going to go down my list a little bit. 3 definitely goes in there. How many times does 3 go into 144? I think it's 3 and 40. Let's say 3 and 48. But let's look here. Let's see. If I have 12 and 12, 12 is really 3 times 4. And this 12 can stay for a second. So 3 times, yes, 48. Okay, 4 times what? 4 is right here times 36. 5 is a no. 6 does work. 3 times 2 is 6, so 48 divided by 2 is 24. 7 will be a no. 8, 4 times 2 is 8, so 36 divided by 2 is 18. 9, well, 9 will work because 3 and 3 is 9, so 4 and 4 is 16, so 9 and 16. 10 and no. 11 and no. So there we go. That's my list. Okay. So which pair of these will give me 13? None of them. So perhaps this does not factor like I thought it would. I feel like I saw 12s and 1s and I was really hoping it would factor. Unless I'm blind and missing something, but I don't think so, right? 7, no. Okay, so if this does not factor, then I'm just kidding. But if it did factor and I could cross a bunch of stuff out on top and bottom, that would be great. Now say I assumed it didn't factor, and after doing the example, I end up getting a 0 in the denominator when I plug in 6. Well, if I get a 0 in the denominator from plugging in 6, that means x minus 6 is a factor. And if you don't know what I'm talking about, rewind it and listen to me again, okay? And that comes from the chapter on polynomials in Algebra 2, and that was something called the Remainder Theorem. So if you want to know what that is, again, I have tons of videos on that. But play that back again, so that's gonna give you a really helpful hint. So if you plug in 6 and get 0, x minus 6 is a factor of whatever you just plugged it into, okay? Well, if I'm gonna plug in 6 then, I'm probably gonna need a calculator because this might be a little annoying. 4 times 6 squared, so it's 4 times 36. 4 times 36 is, well, there it is, 144. Minus 23 times 6, so that was 144. 23 times 6. 23 times 3 is 69 times 2, 60, 60, 120. 9 and 9 is 18. 138 minus 6. Well, 138 and 6 is 144, so on top I get 0. This is probably going to be an okay, because I don't have x minus 6 is a factor of the bottom, I promise. You're not going to get 0 on bottom, and 0 over anything is equal to 0. So I'm telling you the answer is going to be 0 for this. If you don't believe me, 6 squared plus, now I have 13 times 6. Well, 10 times 6 is 60. 3 times 6 is 18, so it's 78. 36, 78. 3 and 70 is 100, 6 and 8 is 14, so it's 114 minus 144. Well, that's the same as the negative of 44 minus 14. I think that's going to be negative 30, and boom, that's 0. There we go, done. Plugging in 0 is pretty easy. Gone, 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 gone. We get a negative 6 on top. We get a negative 144 on bottom. We reduce. Negatives go away. 6 we saw right here goes into 144 24 times. So really you're going to be left with a positive 1 over 24. So that's the answer to the limit. That's the answer to the limit. And now here, plugging in 1. If we plug in 1, you're going to get 4 times 1 squared is 4 minus 23. 4 minus 23 is negative 19 minus 6. Well, that gives me a negative, I meant to say, negative 25. In my denominator, I'm going to get 1 squared is 1 plus 13 times 1 is 14. So 14 minus 144. 144, take away 14, is going to be 130. So this is negative 130. Negatives reduce down. I could reduce by 5. That gives me a 5 on top. 5 goes into 100. 20 times. 5 goes into 36 times. So it's 5 over 26. And there is the answer to my limit. These were all direct substitution. I have no removable discontinuities or infinite discontinuities at 6, 0, or 1, so it makes this problem a bit easier. Next, I have another rational function like we saw earlier, and I'm going to play around with my finding function values and finding a limit here. So if I want f of negative 6, I'm going to do direct substitution. I'm going to fill in negative 6. If I want f of negative 12, I'm going to fill that in, and then my limit we'll do separately. Now, if you can reduce your expression, it might make it easier to plug in after. Even if you can factor, sometimes that makes things easier. So you don't have to raise negative 6 to the third. So I'm going to factor out a 7x squared. That's going to leave me with an x minus 2. And then I'm going to factor out a 7. And that's going to leave me with x to the, 2x to the 4th plus 1. My 7 over 7 reduces to a 1, so that is gone. Now let's work this out. So f of negative 6. Negative 6 squared, if I really show my work, it looks like this. Negative 6 minus 2 over 2 times negative 6 to the 4th plus 1. Okay, so what we have is something simple to evaluate. Negative 6 squared is 36. Negative 6 minus 2 is negative 8. Don't go crazy multiplying, because sometimes you can reduce and it works out really nicely. Negative 6 to the 4th is 1,296. I promise you've seen that before. 1296, does that number look familiar? I promise it's popped up. Times 2 is 2,592. 2,592 plus 1 is 93. Now, this went from being even to being odd. Now, I don't think that this is going to reduce by 8, because 8 is 2 times 2 times 2. 36 is 2 times 2 is 4 times 3 times 3. So unless 3 goes into this, it's not going to reduce. And I really don't think it is, because it's 6 to a power times 2, so it's still 6 to a power plus 1, but who knows? Maybe I'm crazy, but no, I just checked, it does not divide. So what I want to do is 36 times 8. Quick tricks for doing mental math. 8 is 2 times 2 times 2, so 36 times 2, 72 times 2, 144, times 2 is 288, negative over 2593. I'd leave it like that unless it asks for a decimal. Now, plugging in negative 12, it's not like it's going to magically double, because it's double the input. It's not how it works. So I'm going to plug it in the same way. Negative 12 squared, negative 12 minus 2 over 2 times negative 12 to the 4th plus 1. 144 times negative 14 over negative 12 to the 4th is 144 times 144 20736. So it's just 1, 2, 12 to the, obviously a negative to an even power is going to be positive. So this number is 20736 times 2 plus 1. 41473. 41473. And then just figure out what that is. 2016 over 41473. There we go. Okay. Now this last part asks us, what is the limit as x approaches negative infinity? Well, when we're dealing with limits at infinity, that is something we mentioned in videos about the horizontal asymptotes. That is about the end behavior. What is happening way out on either end? Again, this is not a lesson. This is a refresher. So when I want the limit at negative infinity, I have these polynomials on top and bottom. I have a rational function here. You really want to pay attention to the expression with the biggest degree on top and bottom. Then what you can do before anything is you can kind of simplify it. This is not actual algebra. This is just a technique. 7 and 14 both reduce by 7, and then I can cross out x to the third. That leaves me with a 1 over 2x. 1 over 2x is the expression I'm going to work with. If I want to know what happens at negative infinity, pretend you're filling in more negative numbers, like negative 100, negative 1,000, negative 1 million. I'll get 1 over a really huge negative number. So what am I approaching? 0. That's where my horizontal asymptote would be. A horizontal asymptote is your end behavior. So my degree on bottom is larger than the degree on top. My horizontal asymptote's at 0. That means my limit at both infinity and negative infinity will also be 0. The reason my horizontal asymptote is there is because my limits are 0. Okay? So on that note, describe the left and right end behavior of the given functions by the appropriate limits. So this is exactly what I just said. The limit as x approaches negative infinity of f of x will really give you your left end behavior, and your limit as x approaches positive infinity of f of x really gives you your right end behavior. So in either case, what we're going to do is we're going to ignore everything on top and bottom. Now, every professor might show you a different way to do this, or teacher, so I'm kind of just showing you for now my quickest little shortcut for this. So we're going to pay attention to this over here. We're going to reduce f of x more or less when we're dealing with infinitely large things. This stuff is what's really going to control what's happening in our function, okay? I can reduce 42 and 18. It looks like they both divide by 6. That gives me a 7 and a 3. Then I get really x on top. 7x over 3 is really the same as 7 over 3x. 7 over 3x is a linear function with a positive slope. Ooh, sorry, I totally did not even show any of that. So there you go. I promise. There it is. Okay, so that's what we're left with right there after we reduce. So if I want the limit as x approaches negative infinity, as I go out to the left, what am I approaching? I'm going down. So my answer would be negative infinity. There we go. We described the end behavior. How about as x goes to the right towards positive infinity, what happens to y, my output values? Well, it goes up, positive infinity. Alright? This next one I'm going to do in pink over here. This is what I'm working with. 9 and 3, well that reduces to 3. X to the 19th over x to the 16 is x to the 3rd. Well, this is not a linear function. This is a cubic, and it's positive. So the left side, and you know what, let's spice this up a little. I'm going to take this example. Let's pretend this was negative instead. So now it's negative 3x squared. So now I'm looking at this, all right? Or, I know I'm changing it again. Or, let's even do, instead of that being a 16, let's pretend it were a 17. And now this is squared. Negative 3x squared looks like that. So now, end behavior. Okay, totally changed it, sorry. I want to make it as interesting as possible. So this is no more, this is no more, this is what we're working with, okay? As x goes to negative infinity, as x goes to the left, what happens to my y value? It goes also negative infinity. But as x goes to the right, towards positive infinity, where is my y value going? Negative infinity. It's also going down. So you would write an equal sign after this, and then the answer for each of those. And hopefully that clears up some of your limit troubles.